To begin at the beginning. It is moonless spring night in the small town, starless and Bible black. Perhaps a little too dark, sorry. So let me start by demanding some energy services, a little light to see what I'm doing. And this is the start of our story, that I haven't demanded energy for its own sake. I've demanded energy for a use. This is the root of everything we are doing, that everything is springing forth from a demand for an energy service: light, entertainment, cleaning, thermal comfort. These are our used energy services. This is where it all begins. But whenever we demand energy services, we introduce some waste, some lights that are on when the room isn't being used, some heating which is on when the house is empty. And this balance of usable but unused energy and used energy services is mediated through people and controls that manage our light, our heat, our appliances, all serviced by usable energy. But when we want usable energy, we inevitably introduce losses there as well. We have technological losses because none of these devices are 100% efficient. There are inefficient technologies, buildings and equipment that give us technological losses that combine with our unused energy. To get that delivered energy, there's a whole energy system behind it, which has a whole bunch of losses in itself. Energy used to maintain and build the energy system. Energy lost in cooling towers. In the UK, about a third of our energy is lost in that part of the system. And then there's a whole lot, as yet unquantified amount, lost in technological losses and in energy which is usable but unused. And this is the bit we're interested in end-use energy demand. Not the supply system, but this delivered energy through to the energy services demand and the practices that surround that energy use. All of that is end-user energy demand. That's what we study here. And how we study it is epidemiology. It is a study upon the population. Here's John Snow, who worked at UCL, not recently, who published the first epidemiological study in 1855 on the spread of cholera from a water pump in Soho, published in The Builder, an illustrated weekly magazine for the architect, engineer, archaeologist, constructor, sanitary reformer, and art lover. Interdisciplinary work isn't that new. And this is where we do it. We are the RC UK Centre for Energy Epidemiology, which means all of our study is concerned with the UK or this country. We're funded by Research Councils UK. This country turns out to be a malleable, sometimes awkward sort of idea. So often we mean the UK. Sometimes we mean Great Britain because that has a single electricity grid. Sometimes we mean England and Wales because that has a single united legal system and data is collected at that level. Sometimes we mean England because there are a set of surveys that just study England. Sometimes I mean Greater London, the city-state, and then soon we shall have our own independence. But it's a useful unit of study. We're one of 6 centres studying end-use energy demand. We're part of a £35 million 5-year programme to investigate end-use energy demand in this country. Our colleagues at Sussex are leading the Centre on Innovation and Energy Demand, which is looking at innovation practices. At Brunel, they're leading the study on sustainable energy use in food chains. Lancaster leads the study on demand practices, on the social practices around energy demand. Cambridge lead IStute, which is looking at energy embodied in materials and reducing that energy either through lower energy inputs into those materials or lower use of those materials. That's UK in demand. I've got this wrong way around. IStute are looking at heat pumps in industry, so the use of heat and cooling in industry and moving that heat around. So we had a bunch of centres looking at the technology, Warwick Institute and the heat pumps, and then some looking at people, the practices and technological transitions, and we're somewhere in the middle with data concerning both the technology and the people. And data turns out to be an uncertain thing. Observations are sort of messy and all over the place, and some of the things we've been really sure about, like the thermal leakiness of a solid wall, which we've known for 30 odd years, is about 2.1 watts per square metre of surface area per Kelvin of temperature difference. And then that's been a good solid data that we've got a firm grip on until we compared it to reality, and it turned out it was really, really messy. When we look at the population of solid walls, it turns out they've got a very broad range of U values. So here's the one we've been using over here, and the red line is our population of brick walls, and the sort of green and grey line is the population of stone walls, and almost everything is a better thermal insulator than what we thought. But we see a very broad spread among the population of solid walls. By looking at solid walls as a population, investigating the properties, we find out that there were things we were sure we knew that we didn't know at all, and that there isn't a single number that represents what a solid wall is. And that's quite inconvenient, because measuring the thermal properties of a solid wall is time consuming. You need 2 or 3 weeks, you need heat flux centres, and it needs to be in winter. You need a big temperature difference between the inside and outside so that you can measure a significant heat flow. Again, that's a well-known fact, something we've known for quite a long time. And so you can blame my colleague Virginia, who's standing up at the back, for undermining this well-known fact, because she's been measuring the thermal properties of a solid wall in spring and summer with 2 or 3 days or a week. Again, this is something that we're sure we knew, something that turns out to be not true. And this is using statistical techniques right bang up to the 18th century, the Reverend Bayes. And modelling the wall as a simple circuit with 2 resistors and a capacitor, measuring the surface temperature inside and outside, the heat flux, and estimating the thermal mass of the wall and its thermal conductivity with just a few days of data. So this is, here are 6 weeks of estimates, treating 1 week of data as an estimate in its own right, how it evolves over time, 2 different heat sensors, heat flux sensors. As you can see, the systematic bias between the instrumentation is much bigger than the uncertainty using this radical technique. In spring and summer, this is a time when the heat flux is changing direction inside and outside. We've got a very small temperature difference between inside and out. This is one of the things we're doing here, is taking things that have been well known, saying, well, what is the best way to measure this? What if the way we've been doing it isn't the best way? What if there are more powerful techniques? Let's test them, let's investigate, do it a new way, see what happens. One of the things I hope we'll be delivering in 4 years' time at the end of this 5-year project is that we'll have a manual of how to measure things in the best possible way, how to analyse them. So this is a combination of instrumentation and analysis and protocol to get the best available information in the most efficient way. And it's important because decisions get made on data. I mean, often they get made on prejudice and ignorance and bias, and you all know that. But sometimes they get made on data as well, and if we don't have good data, we'll make wrong decisions. We might try to fund large programs to insulate solid walls, which is a great thing and we should be doing. But if we base that on the assumption that it's going to save huge amounts of heat and thus huge amounts of energy because solid walls are really leaky to heat, and that's a wrong assumption, then heads are going to roll. It was still a good thing to do. Uninsulated solid walls are horrible to live with. You get mold, you get unhealthy. They feel uncomfortable. They make for a poor quality dwelling. We should be insulating them. But if you're looking at economic payback over 5 years, you really need to know what the thermal insulation was in the first place. And if it's much better than you thought, you're going to get much smaller savings. Good data is important. And so our data is there for the improving. There's lots of gains to be had because this hasn't been a well-funded field for 30 years. Now the Research Council have put a fairly decent chunk of money, £35 million in for 5 years, to make a difference on policy, to provide support for industry, to save people money, to undertake academic research for its own sake, and to ground further work, to ground the energy models. Models is a fair term. To ground our energy models and models, to put sensible data in, to at least have a chance of getting sensible information out the other end. If we can't measure it, we can't manage it. And we intend to combine all of these and link them wherever possible to create a greater whole, a larger linked data framework containing all the data we have on end-use energy demand as a resource for UK universities as a whole. Part of that is doing data archaeology, digging up floppy drives that have been sitting in a drawer for maybe 20, 30 years. This study from 1973 to 1982. Quite a detailed, comprehensive study. It was funded because we were in an energy crisis at the time, and therefore it was worth spending money on this sort of thing. And the data is in a form that's actually quite hard for us to read now. There's quite a lot of work going into decoding it. And this is teaching us lessons about data management and trying to ensure some sort of future for our data, because of the pain we're having to go through because this wasn't done 30 years ago. And there's some lovely notes in here about how using this may involve the use of computers, and not all users of it may be familiar with the use of computers and their awkward ways. Good to see that's improved. Here's another collection of data, partly from a bit of archaeology, some of it from sort of 1990, 1995, some of it much more recent from 2011, looking at the population of dwellings and their air tightness. Again, not producing a single mean, but producing a range of values from a group of studies to get a much richer idea of the population of dwellings by looking at the differences between how they've been measured, how they've been statistically amalgamated, and how they've been reported. And this leads to one of our research questions about what do we know about the impact that housing stock permeability has on energy demand and indoor air quality. We have some data. Do we know much about this research question? That's something we've been investigating. And its impact on indoor air quality and on energy demand. And it turns out that a lot of other countries have a lot of data. So you've got Norway, Germany, Netherlands, Belgium, all in quite a tight cluster of airtight buildings over on the left. Over here we've got UK buildings and USA buildings, not only with a high average, but a really big spread amongst the population, great diversity across the population. Doing this sort of work is the sort of thing that the medics have really been on top of for a long time. They have the gold standard Cochrane collaboration, a systematic way of doing reviews of data, of combining different studies to find out something about the reality behind each of these studies. Because each of them purport to be studying the same thing, so there must be an underlying thing that each is looking at, just in a slightly different way, through a slightly distorted lens, but each lens is distorted in a different way. By bringing them all together, we can help try and work out what's distortion and what's really there behind these lenses. So one of the things we're looking to do as part of the Centre on Energy Epidemiology is to produce guidance on how to do these systematic reviews, largely stealing techniques from the medics, admittedly, and using them wholesale wherever possible, because they've had a long time to work this out properly, and for them it's been a matter of life and death. And we can take advantage of the rigour and depth that they've developed. So here's part of the work that's been going on so far. There's some of the red top posters around summarised on this work, and I've borrowed these from one of the posters. This is a review of systematic reviews done to help us produce guidelines on how to do systematic reviews. I'm lost, I hope you're not. So, at the pinnacle of all this work, meta-analyses, underline that, of systematic reviews all the way down to case control studies. So here's the sort of thing that is part of epidemiology that we're looking take and port over, to carry over from health epidemiology to energy epidemiology. Case control studies, cohort studies, randomized control trials, appraising individual articles, all the way up to meta-analyses. Taking the techniques that are well established and well grounded, have theory, statistical support, a knowledge base and a practitioner base, and carrying them over to our area, to end use energy demand. Part of this systematic review helps us identify where we've got really significant gaps. There's a very large health study which looks at a random sample of the population and follows them through their lives. You don't know if you are in this study or not. Someone in this room is probably in this study. Your health is monitored through your life, because only by looking at longitudinal data can we unpick cause and effect. A cross-sectional study will give us an idea of the variety in the population, but only a longitudinal study can help us unpick cause and effect, because cause and effect happens over time, years, decades even. We know we have a really big gap on longitudinal data on energy use. And this is an ongoing gap we're looking to fill. That's about as much as I can say for now, but I hope to have more to say on that over the next 6 or 8 months. Somewhere we do have longitudinal data is on how whole countries change their patterns of energy use. So going from left to right in each graph, we've got countries as they increase their per capita incomes. Each of these coloured traces is an individual country as it traces through its economic growth. And all of these have fallen into similar patterns, that as GDP per capita increases, the proportion of energy use that happens in dwellings decreases as a percentage of the total energy use. Industry peaks and then declines as income increases. Agriculture always stays low, but transport increases and seems to continue to increase as a country gets higher wealth as measured by GDP per capita. So transport starts off insignificant, but becomes quite a significant end-use energy demand, something that we have to build into our energy studies. And so that's what we're doing here. Here's, for example, is how energy intensity varies by how freight is moved around. It's a log plot. So here we've got trucks that are using of the order of tons per vehicle. And over here we've got water vessels, barges and ships that are using of the order of carrying of the order of 1,000 to 100,000 tons per vehicle. And the more freight per vehicle is carried, the lower the energy intensity. There's a difference for about 3 orders of magnitude. If you carry a small amount of freight on an aircraft, it's using about 1,000 times more energy than that same freight on a giant ship. And shipping is really energy efficient compared to pretty much everything else because it's moving so much in one go. So shipping gets to be interesting. Finding out where shipping is, what's happened to the population of ships, can tell us something about international end-use energy demand. So here's the pattern of ship movements as captured by coastal stations that are capturing data from the satellite tracking that all ships have. And as you can see, it just follows the coast. If we add in low satellite data, we get a lot more data about ship movements, with some gaps. There's an awful lot of ships turning off their radar when they're close to the coast of Somalia. They just don't want to be tracked. The government ship tracking system has a little more data. It's a little richer. It helps us identify where those gaps are and what's going on in those gaps, which helps build a richer picture of what's happening in the population of ships and their movement. And there is work going on in making ships more efficient through their coatings, through their design and so on. So one of our research questions is to build a database of all of the retrofit that's happening in the vehicle fleet. We're starting with shipping, because we have some data on that already. Well, what's happening, who's doing it, what are they doing, and what's the effect on end-use energy demand? There'll be a database for the industry and for governments on on what works and what doesn't work, what's happening, what's not happening, and where. If that works, if this is a successful exercise, then we'll extend it to land and air transport as well. So here's some of the success stories so far. We've got an assembled a database with some information that's being built out at the moment on where things are happening, the type of ships that are happening, and the sort of things that are happening, routing according to weather, general speed reductions, fuel consumption monitoring, and so on. And all of this is energy demand that's in general happening between buildings. That gives us part of the picture, and the rest of the picture is within buildings themselves, and then there are trade-offs between what's happening between buildings and what's happening in buildings. People who are working from home are moving some of their energy consumption from the journey to work to some of the energy into their home. That's a complex relationship because you've got changes of energy use in their office, which now has a lower occupancy, changes of energy use in their home, which now has higher occupancy, and changes of use in the transport system, where there are fewer commute trips but maybe more other trips to compensate. These are complex interlocked systems. And it turns out we have quite a lot of information on what's happening between buildings in end-use energy demand. But within, for example, the non-domestic stock in offices, factories, commercial premises, we have much less information. We've got a big gap there. In fact, we don't really have a good picture of what buildings are where and what activities going on in them, which is quite odd because you can at least go out into the street and see what buildings are where. And that's part of the validation work that we're doing, so we've used Camden as a first part of our study to work out what activities are going on in which buildings, producing a 3D map of activities in buildings, in the building stock as a whole. But the data is very, very messy, very convoluted. Dwellings are relatively simple. You have a building, and that might be one dwelling, or it might be several dwellings. Non-domestic premises are really more awkward. You might have one company which is spread across several buildings on the same campus. You might have one set of premises that is split across two conjoined buildings, like this red shop here. But in the same block, you might have a different set of premises which is separated across different buildings. And there isn't really a map of how all of these activities are spread out within the physical stock, within the three-dimensional stock. And so part of the work some of my colleagues have been doing is mapping the things we do know, like the building floor prints, the footprints that we can get from the Ordnance Survey, and information on the square meterage of activity that the Valuation Office collects in order to tax them, and the heights of buildings, and combining this to infer where activities are going on, which activities are going on in which parts of buildings. And mapping address points and electricity and gas meter numbers onto those buildings and onto those activities to give us an idea of what's happening in the population of buildings as a whole. We then create energy models to work out, to infer the things about energy use that we don't know, that we can't get from the meter readings. So if the meter readings are quarterly or annually, we can infer things about the diurnal profile, the variation within weeks, from what we know about those individual activities and the sort of buildings, the size of buildings, the location of buildings where those activities are going on. And from there, we hope to build a 3D map of Britain, but of Camden at first, it's around Mornington Crescent Tube, with all of the activities mapped onto their floor spaces, the individual activities going on in each of those. But we need information on how much energy use is happening for each activity type. There was a landmark study done by Sheffield Hallam in the mid-90s, which is still our best available data on how energy use varies by industrial activity type. So that's nearly 20 years old. It's the best we've got. But we've got an exercise in asking companies to volunteer their energy data. It's a whole bunch of interesting problems around self-selection bias and non-representativeness. But at least we've got case studies, and ideally we'll have a lot of case studies, all of which tell us about something real about energy use happening there that we can map onto different activities. And we're already starting to get results from things like the display energy certificate. We are seeing reduced energy intensity across different building types, university campuses, clinics, workshops, over time. But the baselines differ, the reductions differ. Lots and lots of information about the population of schools. So here's the distribution, the cumulative distribution of intensity of energy consumption for secondary schools on the red line and primary schools on the blue line. This tells us something about the distribution of energy use within the population of schools. And the hope is that if we can get all this information about detailed activity types and their end use energy demand by activity type, and where these activities are happening, how much floor area there is, and where those activities are, we can build a stock model of the entire non-domestic stock, an energy model which will be able to test the potential impact of new technologies, of policies on that big industrial commercial energy demand. By putting together small pieces of the big picture, we hope to build a cohesive picture of what's really happening now and how it will change. And this raises a very thorny question of what is the purpose, what is the role of modelling. And we've had the great luxury in energy modelling for 30 or 40 years that no one has prodded our models too closely. No one has really tried to pick them apart in the same way. It hasn't had the same scrutiny that the medics have had. Again, their models are a matter of life and death. There's a lot riding on it. And we're looking to see if we can raise our game to the same sort of standard. When you publish in the BMJ or the Lancet, if you've been doing a modelling study, they have someone here can maybe tell me, 15-20 page checklist on tell us everything about your model, give us a complete audit trail of what you modelled, how you modelled, why, and so on. And we're looking to build our guidelines internally around that to raise our standards to best practice. It's a game changer. It places huge demands on us, but we think the gains are really worth it in terms of giving assurance on how these models have been developed and how they can and should be used. And here's an example of how they can't and shouldn't be used. This red line is what the models have been telling us about how energy demand varies from very new buildings to pre-20th century buildings. So pre-20th century buildings should be using loads of energy according to this red line from the model, and new buildings should be using much less energy according to the red line from our model. The blue line is observed reality. And this big narrative that older buildings are sucking out much more energy just isn't really borne out as much by reality as we thought it would be. There are other things going on. And using epidemiological techniques, we can start to tease out what else is going on in there. So if we want to know how does the age of the property impact on its energy use, and whether we can characterise the efficiency of a property better than our existing models, we can start to unpick things like how many energy efficiency measures have been deployed on particular dwellings, separate out the confounding factors. How much is it to do with region or the number of bedrooms, or whether it's owner occupied or socially rented or private rented, the year it was built, whether it's semi-detached or terrace, and separate that out by fabric efficiency measures and boiler measures, boiler replacements, and heat pumps and so on. And so this very detailed study helps unpick a lot of these factors and puts confidence intervals around each of the scales of impact. So where the confidence interval crosses our line here, that means we can't really say much about this factor. It's not really telling us much about whether this type of, whether dwellings with this attribute are more or less likely to have energy efficiency measures. As you can see, very few of these confidence intervals cross this line. We've got an awful lot of significance. We've unpicked a lot of the confounding factors on how many energy efficiency measures are deployed in the stock. And there's a lot going on about the year of build that is significant, that does change whether people are more or less likely to put in wall insulation or replace the boiler and so on. But there are other things going on with internal temperatures, because that's a big driver of how much heat demand you've got. The higher you set the thermostat, the more heat you're going to use, obviously. But what if different ages of dwellings are trying to get to different temperatures? What if people are just behaving differently with their heating systems, with their thermostats? What relationship is going on there? There is something going on. Pre-20th century buildings over on our left have lower temperatures for bedrooms and living rooms. Newer buildings over on our right have higher observed temperatures. There could be two things going on here. People in newer dwellings are choosing to be warmer, or they're just able to be warmer. The combination of the newer building and a newer heat system is able to get the dwelling warmer than it otherwise would be. But this has significance for the model, which would assume that the internal temperature that each dwelling was striving for was the same regardless of the age of dwelling. Here's empirical data to give us information about different subsets of the population, to break that down. Which leads us to a research question about the prevalence of very high heating demand and very low heating demand. What's going on in these two segments? Are these paragons of very energy efficient dwellings and people that we should be aspiring to, or are these people who are just going to die of hypothermia? Are these really profligate people? Are they living in tents effectively with 3-bar heaters on all the time? What's going on? By unpicking what's going on in different segments of the population, we can learn much more about energy demand and the systems and practices behind it. So here's a bunch of observations from many days on a single dwelling. On the x-axis we've got external temperature, so it's a nice comfy 20 degrees on our right and getting down towards freezing, but not out freezing on our left. And roughly speaking, as it gets warmer outside, it's warmer inside. No kidding. But that's not how your thermostat should be behaving. Your thermostat is supposed to be there to maintain a nice stable temperature regardless of what's going on outside. That's not what's happening. We've got this slope going on, so if we just throw a straight line and see what it looks like, we get some idea of a characteristic property of this one dwelling. Is this dwelling representative? Is this something that we see across a lot of dwellings? What does the population, if we look at a few hundred dwellings, what can we learn? We can maybe win a Turner Prize for what's going on in these dwellings. And a lot of complicated things is going on. I've got a dwelling here where the colder it is outside, the warmer it is inside. That's probably quite a nice dwelling to be in. Quite a nice way to do things. We've got an awful lot of dwellings with completely different slopes. We've got a mess. We've got a very complex picture. We have a population with a great deal of diversity of behaviour and of diversity of fabric and diversity of heating systems, all giving very different results. Here's another single dwelling, each observation I think 1 hour, so across a whole bunch of days over a year, on how heat consumption is varying with external temperature. So okay, no surprises, the colder it is outside, the higher the heat consumption, and once it gets to about 15 Celsius outside, the heating's turned off, and our residual heat consumption here is just for hot water. Everything here is probably space heating, or it's increased hot baths as it gets colder outside. But we've got quite a nice, clean, orderly relationship, quite a lot of diversity around the line, but an underlying gradient of how heating power and external temperature are related. A fairly simple parameter to summarise the heating behaviour of this dwelling, which is capturing everything about the fabric and the behaviour and the occupancy and the efficiency of the heating system and the operating patterns of the heating system, all in this line, all in the power temperature gradient. And this is something that's partly come out of the work of one of my colleagues, Jenny Love, who inspired us all by drawing a 5-dimensional graph. Again, something that we were assured was impossible. Jenny carried off with a plum, which we then boiled down to a single parameter of power temperature gradient, how heating demand changes, how many watts of extra heat the building requires for every Kelvin, every degree Celsius change in external temperature. And that gives us a research question to explore this power temperature gradient, this beautiful summary that encapsulates so much about a single dwelling. It throws away a lot of really important information as well. This isn't the only benchmark we use, but it's a new way of encapsulating a lot of information about a dwelling in a single statistic. And we can look at patterns of how this power temperature gradient changes for very old buildings on the left, very new buildings on the right. The entire Cambridge Architectural Homes Heating Survey is the top line, and just a collection of 3-bedroom dwellings is the lower line. Summarising information about populations and subpopulations in statistics in new ways, looking at old data in new ways, looking at new data in new ways. So here's the population of dwellings split into 5 groups. Here's at the bottom is our group 1, our dwellings which are least responsive to changes in external temperature. And when it's pretty warm outside, they're using very little energy. Even when it gets to 5 degrees below, they're still only using 5 kilowatts for heating. That's pretty low. Our dwelling, so not only are they less responsive to heating, but they're lower users altogether. And that's a pattern that repeats across all the groups. And so here at the top we've got our highest users, and they're really responsive. The colder it gets, they really start sucking energy out of the system. This is 11 kilowatts. That's a huge amount of energy to be channeling into a building. And because the residents aren't cooking, we know that energy is going pretty much straight out of the building as well. And here are those 5 groups and what's going on with each individual day. For our lowest energy users, we've got a much flatter curve over the 24 hours of the day. For our highest energy users, we've got this huge lunchtime demand. You still see the morning and evening peaks, which starts to help us unpick questions around how the daily load profile, how the diurnal distribution of heat might be fine-tuned by someone using time of use pricing, which helps ration a resource which might have different scarcity during different hours of the day. At the moment, gas is very forgiving as an energy vector. It's very easy to store natural gas. The distribution system itself stores a huge amount of gas, and you can play tunes with the pressure in the system to change the amount of storage, and it gives you a buffer in the system. And it's a very dirty, unsustainable way to heat our homes, and any of the clean ways tend to have much smaller buffers. And so this diurnal distribution really matters. And as the temperature changes outside, the diurnal distribution changes. And that matters as climate changes, because we will have different patterns of temperature outside. There is a much bigger picture here going out to 2030, 2040, 2050 as external climate changes. The diurnal patterns of our energy and the total amount of energy we use will change. Our systems will need to adapt. Which brings me to one of our biggest collaborations with the Lancet. This is our second big commission with them on the biggest global health threat of the 21st century, climate change, and delivering a healthy planet. So it's a big multidisciplinary study combining everything we've learned so far on energy and climate and health inside dwellings to give us a picture of where are the biggest risks and where are the biggest mitigation opportunities as climate changes, what are the best ways to mitigate that climate change, and what are the opportunities and the needs to adapt to it. And then there's a bunch of other collaborators as well. Almost all the work we do is involving external organisations of one kind or another, who are providing data, providing skills, providing services, providing analysis, providing introductions to people who have data and so forth. And this is who we are. I'm one of 14 staff who are paid for by this research budget. In addition, we've got other members of faculty who work on this project as well, our management team. We've got David Shipworth, Bob Lowe, Andreas Schaefer, and the Institute Director, Taj Reshtin. If you spot any of these faces here this evening, they'll be great people to go and ask questions to when we go for wine and nibbles next door in a few minutes. They're the ones who know. My job is strictly to, apparently my job is to help guide and steer the research direction of a collection of academics. As many of you will know, that involves cat herding and being something of a human shield. And it's a fantastic job. It's a huge joy. And that's why I do it. These are my goddaughters. I probably won't see 2050 or much beyond it. They will. I've got a lot out of human civilization, on the whole, when it averages out. And they should too. You know. So that's why I do it. And this is what we do. At least that's been a quick romp through what we're doing for 5 years' time. I'll try and take questions now, but what I think I'll almost certainly do is defer to my colleagues in the room, or I'll hastily point you to the food and wine which is next door. Thank you very much for listening. Thank you very much for hearing out my introduction to energy epidemiology, and please bring your questions. You all want food and wine.
Andrew, could you say a bit more about the power temperature gradient concept? Because I'm interested in sort of how that could be used, or how it would be made meaningful to consumers. I mean, we what you sort of alluded to is that, once or twice, is that, you know, the way that the policy framework looks at the performance of dwellings is in terms of the sort of EPC, it's a fabric rating, and it's sort of standardised and probably not really accurate, and it doesn't really take account how people use buildings.
Yeah.
And you know, there's another way of looking at it, which say, well, okay, let's look at human behaviour and, you know, try and reduce waste, and then you talk to people about how they use energy. But that is sort of in a way disconnect. The two things aren't really joined up. I mean, does the power temperature gradient join the two things up and give you a way of saying to people, you can either, you know, it's a combination of the property and what stuff you put in it, and how you use it, and what your practices are, and therefore you can use this as a sort of as a communication tool, if you like. Is that where it's going?
Well, that's one of the uses of it. So it differs from things like EPC ratings in two ways. One of the ways is that it's grounded in empirical data, which is one of the things that we're trying to put at the core of energy epidemiology. It's grounded in empirical data. And the other thing is, yeah, as you say, encapsulates behaviour and the heating system efficiency and the fabric efficiency. So it's a way of conveying how all three of those have worked together to produce your heating demand, your heating bill in the end. So it gives us a good, useful analytic tool. It gives us a statistic to summarise the behaviour of the entire dwelling system, both the technological and the human. But it does hide how much each of those three roles plays of behaviour and fabric and heating system. But we do know we can say things about, well, if you change your fabric in this way, if you're putting your triple glazing, your wall insulation, your floor insulation, your loft insulation, you will change it in this way. And if you change your heating system, you will change it in that way. And if you change your behaviour, you'll change it in that way. We can draw deductions from our models of how changing those individual components will change the big picture. We can't separate out those individual components for a single dwelling, but we can explore how changes to them would change the heating bills. I'm not sure it's got legs as a communication tool. Something we really haven't tried yet. It's a new statistic for encapsulating a dwelling's behaviour and performance, and we're just exploring its power and use at the moment. Yeah. Thanks. Okay, I see 3 hands, and let me take them in order from front to back.
Funny enough, I was talking about this earlier to a colleague, but to what extent are you also factoring in or otherwise considering unintended consequences of things? For example, improving insulation and increasing overheating, or incidences of overheating. So is that part of the study as well?
Yeah, for example, one of the places we'll do that is in particular case studies, which are a really good way to capture things like this that might not be apparent at a population level, but are a good way to capture all the things you weren't expecting to see. The challenge with large population studies is you tend to have quite a structured way of collecting data, and you miss the things you weren't expecting to see. With case studies, both in medicine and in energy, gives a way to capture this whole range of behaviour. So we're looking to incorporate best practice in case studies as well as in population studies to help give us clues about what's going on in unintended consequences, and it's something that several of our PhD students have picked up on. So I don't have any posters to show you here yet from C on unintended consequences, but it is very much work in progress. There are a whole bunch of posts. All the red top ones around here are the C work in progress with results. So please help yourselves spend some time with those as we finish this session. I'll take Paola then Prashant.
Thank you, Andre. I was just wondering whether you could say a bit more about the role of data collection in this whole process, because surely data collection is kind of the first part you need to do in order to analyse anything really. Now, I'm working with non-domestic buildings, for example, and the feeling is that very much the data collection is a big part of the problem.
It's a huge part of the problem. As some of our students here will attest, I do try to scare our students on arrival into just how messy and awful data collection is, because it's very easy to come in with the idea is, well look, we'll just collect the data and then the really interesting hard bit starts about analysing and making sense of it. But it turns out that just collecting data is this incredibly messy, awful, complex thing. There is a set of guidelines on how to monitor energy use and its related attributes. That's quite old now. It doesn't really represent what we know of as best practice, and also we're evolving best practice, as I said, on measuring thermal properties of solid walls. So we are looking, one of the things I'd like to come out to see is a handbook on how to collect data well. One of 20 papers I've somehow never got round to finish writing yet is called 100 Ways to Collect Crap Data. It started off as 10 ways and asked people for ideas, and it hasn't stopped growing yet. But I think that's another useful thing we can give back to the academic community, is the guidebook on how to collect crap data, because we've got really good at it and we ought to document that. Prashant.
That's a fantastic presentation. I really loved your power gradient idea and the facts are sort of grounded in real life data. My question is actually quite similar to Michael's, because in a way you showed a very powerful graphic showing how the power gradient, temperature gradient was affected by age of building. I was wondering the extent to which you believe that other things might be sort of confounding those results. For instance, older buildings tend to be more terraced or have different typical average sizes. Those kind of things might be just kind of correlated with age.
Absolutely, absolutely, and that's why we've got let me pretend this bit's deliberate. That's why we have a coherent program of different academics going off in different directions, doing different things that are loosely connected, is that we can build a big picture, a whole, which is all about bringing together the study on confounding effects of what attributes affect which properties are more likely to have had energy efficiency measures. And this other study over here about how internal temperatures vary with age of property and behaviour of occupants, and this study over here about how heating demand changes with changes in external temperature. So at the moment, because we're only 1 year in, we have this luxury of a 5-year study. We can just try and get individual pieces with the intention that we will be able to make a jigsaw at the end of it. So we have different studies that give us insight into this very question. And I'm really looking forward in 3 years' time to when we can synthesize it into a whole. A lot of these studies are only a few months in, so it's very early days for any of them. We do have preliminary results, as you see. But yeah, the idea is that we get insights into enough aspects of the system as a whole that we can start saying things about how all of these interlocking things really do relate and break down the individual contribution components. Yeah, and that is where we're going. Okay, I saw 2 more hands, and then I'm thirsty, so we'll go for one, and I'm sure you are too. One was us, so there, and finally there.
Given the origins of epidemiology, how interested are you in the effects of decision making in the system you've described on health, and vice versa? I mean, are you already studying fuel poverty? Are you looking at what might become the incidence of cooling poverty? And the other way around, as the population ages, how does that impact on the system that you're talking about? What about regimes where people bring home babies? What happens to them when they're trying to create that set of conditions, which is quite unusual, but actually exercises people a lot?
Yeah. So one of the things is that the Centre for Energy Epidemiology isn't trying to do everything, thankfully. And so we have our 5 sister centres. So Elizabeth Show's centre based in Lancaster, the Demand Centre, is looking at social practices and how things change, how practices evolve over years and decades, and how cohorts change, and so on and so forth. And so part of that will hopefully cover some of those questions about what happens as the population ages. On the question of health and the relationship between our interventions and health, for the first couple of months of trying to explain what energy epidemiology was, I had the luxury of saying, look, we're using techniques about health, but it's not about health, it's about energy. We're applying it to these things over here. And that was nice and simple. You could get people off health and onto energy, just those techniques, this subject. And then we started looking at the impact of mould and dust mites on health, and the impact of climate change and climate change mitigation and adaptation on health. So all of a sudden I'm back over here saying, no, we do look at health, and we do health epidemiology work as well. And we work with health epidemiologists at the London School of Hygiene and Tropical Medicine. We've got this Lancet Commission on climate change and health. So it turns out that we are doing a whole bunch of health where we bring our energy epidemiology and sit next to health epidemiologists. And they do their bit and we do our bit, and we look for insights into the same system and where the interventions are having positive and negative interactions with the health of the population. And finally, I won't keep you from your wine and nibbles any more after this.
A quick one. There was a bit at the beginning of the talk where I thought I might have drifted off into some sort of fancy daydream land. A 3D subsectional model of every building in the country.
That's right.
Within 5 years and only 14 people. How aspirational is that?
Oh, they're good. They're really good. Yeah, we hope to have it for Camden in the next few months. As Camden is really easy, because validation is really easy, because when we're not sure what's going on in a building, we go outside our door and look. We won't have that much luxury with all the other places, but the idea is that will give us enough heuristics and enough techniques to be able to draw inferences from the limited data we do have. And extensive use of Google Street Maps to take virtual walks down streets and look through windows as well. Let me get back to you in a year or so about how ambitious that is, but our matching rates for meters and activities and buildings so far is of the order of 97 to 98%, and my colleagues are really frustrated because they know they can do better. So at the moment it's looking really promising. Camden is obviously atypical once we want to go further, but that is the ambition, and at the moment it does look like a realistic ambition. Yeah. Thank you again very much for your time. Please join me next door for wine and nibbles.